Hello and welcome again to this video series. In this video we will be looking at uninformed search, and in particular to the algorithm known as the depth first search, or the DFS. Okay, so we covered the breadth first search. Now let's cover the depth first search. So the depth first search is an algorithm that is similar to the breadth first search, where it's trying to find a goal that is inside a graph or a tree that we'd like to explore. The depth first search it has a different methodology than the breadth first search. Okay, so the depth first search is basically expands the deepest node in the current frontier of the search tree. Okay, so it takes a path. For example, the same example that we have given, if you're standing on an intersection that has like 6 roads coming to it, and you would like to find something that is 7 or 8 blocks away from you, what you do is, in the breadth first search, we said you go to explore of depth of 1. Basically, you go 1 block away and search for each road. You go 1 block away, and then you keep expanding the radius of search into 2 blocks, 3 blocks, 4 blocks, 5 blocks until you reach the goal. The depth first search takes a very different approach, and it actually goes and says, well, let's take the road entirely to the end, and then if we don't find it, we come back and try another road. Okay, and that's basically the difference between the breadth first search and the depth first search. So if you have something like this going on, okay, so you have your source, you start from here and you want to look for the goal. What your depth first search would do is we'll take the path of A, and then we'll go to B, and we'll go to C, we'll go to E, and explore all of this. And it's gonna then do a backtracking, and it's gonna come back and then go to the closest fork to the first edge that it found, or the first leaf that it found, and then come back and explore that, and then when it reaches the goal, it should stop. And that's basically how the depth first search works. Okay, and in graphical representation, this is how it actually works. So you start with S, and the S has 2 children, A and B, and what you do is you explore A only, and when you explore A, you get the children of B and D, and then you explore B only, and when B is explored, you find the child C, and then C is explored only, and then the child C, you go to E, and E is explored, and then E doesn't have children. So what we do is we backtrack until the last fork that we have, so the fork was at an A, and then we go and search, and we find the D, and from the D we find the G, and the search algorithm should stop at that time. And this is very important. In the breadth first search, there was no backtracking, but in the depth first search, we go dig deep, and then when we don't find the answer, or this, the goal node, we backtrack to the closest fork and then try the other path. If we couldn't find it, we backtrack and go to the other path, and this is how we do it. Now, in the algorithm of depth first search, we always start from the left. Okay, so if you have a tree and you always explore the node that's on the left before the node that's on the right. Notice for A, we explored A before B, and over here in the B and D that are children to A, we explored B before we explored D. So it's always the left child that we explore first, and of course these children are appended in lexical order, and hence we find the lexical order is the same thing as finding the left node, and that will make sure that each one of you, if you have a graph, will generate the same tree. Okay, so we repeat all of these backtracking and searching steps until we find the goal. Okay, and this is the idea of depth first search. Okay, so the depth first search, we are going to use a stack to implement the depth first search, and stack is quite different than the queue. The front of the node that is on the that's going to be explored is the stack head, so we're only going to work with the head, and it's going to take 3 inputs: the graph, the node that we want to start from, the node that we want to go to, okay, the goal node, and then the source node over here from S to G. It could be from any node to any node, but the algorithm goes from we need to give it where to start from and where to go to, so this becomes the root node. Sorry. And if the goal is reached, it returns a success. Otherwise, it returns a failure, and if it returns a failure, we want to be sure that that goal is not within the tree that we are searching. So we want it to be basically a complete search. Okay, let's go and look at the algorithm. So the algorithm is very similar to the algorithm that was explained in the breadth first search. So we start with initializing our extended node to 0 and the enqueued node to be 1. So the extended node is 0 and the enqueued node to be 1 because we enqueue, as soon as we start, we enqueue S into the stack. So we take the stack and we put the S into it. And then what happens is well, let's come over here. So in the stack, basically we check if the stack is empty or not. So stack is not empty because we just added the root into it, and we check the head. Okay, if the head is the goal, then we are done. We return a success. If the head is not the goal, we generate the children of the head. Of course, we extended that node, so we add 1 to the counter so that we can count how many nodes we have extended. We delete the head, okay, and we insert the generated children to the stack, not to the queue, to the stack that's over here, and that is gonna be inserted in, of course, as in lexical order. But notice this is a stack, and in the stack things stack up, okay, and the head becomes the latest thing that you actually inserted into the stack. And you also go and add to the counter that we have for the number of children's added to the enqueued node. So how many nodes have been enqueued inside of this stack, okay? And then you keep repeating this until you find either the goal or the stack is empty. If the stack is empty, then you basically do not have the goal inside the tree that you're trying to search, okay? But we'd like to stress that you have to insert everything in lexical order, okay? So let's look at how the stack works and what's the difference between this and the breadth first search, okay? So let's take the same example as the breadth first search one, and we have the same tree that we are going to be exploring. Of course, this is an uninformed search, so the depth first search algorithm does not have information about this tree, and it's going to explore it one at a time, okay? So we're going to start and we're going to put the S in, okay? So once we put the S in, let me take a pointer over here. Where's the pointer? Yeah, laser pointer here. So let's start and put the S in, and then what we do is we extract the S. That's the head of the stack, and then we delete it from the stack, and then we generate the children of the stack. The children are SA and SB, and again, the depth first search does not take care of the weight. It ignores the weight, so we put A and B, and we insert these into the stack in lexical order. And in lexical order in the stack, it'll be an SA and the SB. So the head of the stack will be SA, and the bottom of the stack will be an SB, okay? So that's how we're going to insert it to the stack. Now, the next time we're going to go and we are going to take the SA, and then we're going to delete the SA from the stack. So we will only have the SB in the stack. And we're going to generate the children of SA. So the SA will have the SAB and SAD. These are the two children that we'll have. And we will append them in the stack in lexical order, okay? So the SAB have to be at the head of the stack or the left, so we insert the B before the D. And notice when we insert in the stack, we insert on top of whatever was there. So the SB was there, we do not shift it to the head, we keep it there, and we insert it on the top. If you remember what the stack was, let me take a pen over here, and the stack was nothing but something like a container that has different levels in it, okay? So this is the different levels, and whenever the new element comes, it falls and sits over here, so it's at the end. And if there is another element, it comes and sits over here. And when you extract an element, so this element will go out, and you can actually put it over here, and then that's the head actually, and you have to delete it from the stack basically. And then when the third element comes, Okay, the third element comes, the element number 3 will be here. And if there's a fourth element, it'll be here. And when you extract, 4 was going to come out, notice. And then the 4 is going to be erased from the stack because we delete the heads. And then when we add something into it, and 5, so 5 is going to come over here. And then depending on the type of process that we're doing, notice the stack is filled that way. So instead of filling the stack this way, what we do is we write on the head of the queue, actually, that makes it a stack. So if you take the queue and write from the head, instead of appending at the bottom, the queue becomes a stack, and we add to it the SA and the SB. Okay, so SAB and SAD, that's what we're going to add to it. So this is just a previous review of the stack and how it works. And this is basically the example over here. So once we expanded the SA, we got the SAB and the SAD. We added the SAB and SAD, notice in lexical order, B before the D, we added them over here. Okay, then what we're going to do, we're going to extract the SAB and we're going to delete it, and SAB, notice we extract this B, and then we're going to append the children into the head. Notice SABC, we're going to append it to the head. It's going to come on top of the other ones, so it's going to be the first one. And then we are going to extract this and delete the head, and then get the child of the B, which is the C over here. So SABC is going to come, and then SABCE is going to come. And after we extract this, okay, after we extract this, there are no children, so what we get to the E, and there is no child for E when we extracted that. So we backtrack and go over here, and we want to explore D. So to do the backtracking over here, you have to do nothing. As soon as you reach to the E, you just delete the head, and that's it, you stop. Now notice this thing will become your stack, and this will become the head, and that's what's shown over here. So now we have the stack, and we take this and explore it. Okay, and when we explore this, we get SADG, and we add this to the stack. So the stack we add always on the head. So notice the SADG is over there, and next time we pick it up, when we extract the head, we are at the goal. So the goal is at the head, we stop. That's it. Okay, so this is how the depth first search is actually working. It's a pretty simple algorithm. It tries to copy the behavior. So we were trying to copy the behavior of the depth first search using a stack. And when we changed the queue to a stack, notice everything became pretty simple, and we just have to extract the head and look at the node and insert the children in the queue head or into the stack. Okay, so they're going to become the head in lexical order, and that will guarantee for me that I follow the steps on the same graph that I have. Okay, so this is basically the depth first search. The number of extended node is 6. So notice I extended S, A. So I extended S, SA, SAB, SABC, SABCE, SAD. Okay, I extended all of this. So there are 6 nodes that have been extended. How many nodes have I appended? 1, 2, 3, okay, 4, 5, 6, 7. Okay, and then we deleted this, so there was no appending, and then we extended SAD, so we got SADG, so that was the 8th one. So we have 8 enqueued nodes, 8 nodes entered into the stack. Okay, and then the path that it suggests is SADG, so it's SADG, that's the path that it suggests, and the cost is 11. Okay, so this is a simple example where you can understand how the depth first search actually works. Okay, now let's go to the next example. This was another example that we solved. Let's solve this using the depth first search. In the depth first search, we start with the initial state S, okay, and then after S we append the children. Okay, so it's SA, SB, SC, so we delete the S and we put the children, so it's a stack, and we observe the lexical order, and then we extract SA and then append the children of SA, which are SAD and SAE, but they will be appended at the beginning of the queue, so it becomes a stack, so SAD and SAE, and observe the lexical order over here also. And then we are going to have this basically the content of the stack, okay? And then we extract SAD, and SAD, when we extract it and try to generate the child, we will find that there is nothing there, so we delete the head and then move this to become the head of the queue. That's our backtracking. And then we got SAE, we expand SAE, we also backtrack because there is no child for SAE, and then we get SB, so we generate the children of the SB, so we get SBF, so this is the SBF and the SBG, we get these two children and we add them, SBF and SBG. Observe the lexical order here again, F before G, and then we come back and take SBF. There is no child for SBF. As you can see, F has no children. So it basically removes itself and the SBG comes into the head. And then we stop because we have reached to the goal. And in this case, notes the number of extended node is 6. The number of enqueued node is 8. And the path is SBG. And the cost is basically 2 because we assume that all the costs over here are 1. Okay, so this is an example, and you can see the depth first search is quite simple and easy in comparison to the breadth first search. It dives deep, it goes deep inside and backtracks, deep inside and backtracks. Okay, so it has its benefits sometimes, but sometimes its breadth first search might be better than depth first search, and we'll talk about that at the end. Okay, so this is an example, and this is the third example that we talked about. So we have over here, we're going to start from S again, and from S, notice now from S, I am going to go A, B, and C. So I'm going to add SA, SB, and SC, and then I'm going to take the SA and expand it, so it's SAD. Notice SAD, and then I'm going to expand the SAD, so it's SADG, and I reach the goal, so I stop. Okay. Now notice in this example, in the breadth first search, we found the path is going to be SCG, whereas in the depth first search, we found SADG. Of course, different algorithms will propose different paths, okay? And none of these algorithms is looking for the best path. It's looking for a path from S to G, and they don't care about the cost. So each algorithm has different steps, and different steps will result with different answers, and that's fine. Okay, so this is how the depth first search is working. Let's go to the next slide. So let's talk about comparison between a depth first search and a breadth first search. So the breadth first search uses a queue, whereas the depth first search uses the stack. It's the same algorithm, but we change the queue to a stack, and it becomes from breadth first search to depth first search. And this is the power of using a good of using the stack and the queues, which are data structures. Okay, so if you're using a good data structure and you have a program, if you just change one thing to another, you went from breadth first search to a depth first search. Okay, so the breadth first search can be used to find single source shortest path in an unweighted graph. So if your graph is not weighted, you will find a single shortest path because it is unweighted. The depth first search might traverse more edges than the breadth first search, depending on the shape of the graph or the tree that are you searching. But it will not guarantee you the depth first search in any case that this is the best path that you can actually get. But the breadth first search, if all the weights were similar, it will find you the best weight, okay? Because it finds the shallowest path, and that will be equivalent then. And the breadth first search is more suitable for searching vertices which are closer to the given source. This is one of the examples that I gave. If you have the 1 millionth grandfather tree and you wanted to search for your sibling, breadth first search is not good. In fact, depth first search might be better because it's going to dive deep inside and look at the leaves, and the leaves are your siblings most probably, or very close to your siblings, and then you try to go up and try to search, and if not, go a little up until you find your goal. Okay, so in that case, depth first search is most suitable. So if you have a large tree and very deep tree, and you know that your answer lies in the lower end of the tree, then depth first search is a better algorithm to use than a breadth first search. Whereas if you know that the answer would be on the top layers, then the breadth first search will beat the depth first search. Okay, so these are some sort of tricks on when to use which one when you're doing search. Of course, both of them ignore the weights. They do not take care of the weights. The only time the breadth first search takes care of the weight is if all the weights are equal, but those cases are very rare actually in real life applications. So you always find that the weights of anything that you want to do are different. Okay, so with this I will end this video lecture. I thank you for watching this video, and I hope to see you in another recording soon. Bye bye.